class. So today we'll be looking into our module 5 syntax directed translation. The contents goes in this way. So in the previous class we discussed about the syntax directed definitions, syntax directed translations. We also looked into few one of the problem where how exactly the data will be transmitted from one node towards the other node, right? So a lot of you people had doubts in it, so let me clear it off by taking the topics again. So syntax directed definition, similarly it's of a, like with respect to the context free grammar, it's a definition of a given CFG with attributes and rules, and attributes are associated with the grammar, symbols and rules with production. So attributes may be of many kinds. One might be a number, type, table, etc. Right? It can also be some of the property within the given grammar. So which grammar are we speaking about? Context-free grammar here. So two types of attributes here. One is synthesized attribute and the other one is inherited attribute. Synthesized attribute and inherited attributes has few differences which you need to understand before, right? So synthesized in the sense where the value it can get from itself, and it can also get the or push the value from its to its child, right? So synthesize is where the value which it can get itself and it can push the value to its child. So a synthesized attribute for a non-terminal at a parse tree node n is defined by a semantic rules associated with the production of n. Note that this is important. The production must have its head. A synthesized attribute at node n is defined only in terms of attribute values at the children and by itself, right? So if you look into the term here with synthesized, I have a node and I have a child node for this main node. Let's call this node as A, and this is B, this is B, and this is C. So synthesized attribute, what it tells is, if this is synthesized, if I take this as A dot synthesize, it can get its value from itself. That means if I have any inherited value here for A dot inherited, right? If I have A dot inherited here, so from inherited it can get the value to itself, and the other thing is it can push the value to C dot synthesized. So the value can be pushed to its children. That's what the value or the attribute value can be pushed to children or at itself. That means I am getting from inherited towards synthesis itself. This is something called as synthesized attribute. Similarly, if we go with respect to the inherited attribute here, inherited attribute works in a different way, right? Similar to that of synthesized. So here how exactly it works is, if I have a particular root node here and if I have one child and second child, so this child is B and this child is C. The case is, so as I said, my inherited value can get the value from its parent. So let me speak with respect to C dot inherit here. So if I have C dot inherit attribute, I get the value from its parent or from its sibling. Getting? So this C dot inherit can get the value from A dot, yeah, that's the question, A dot synthesized here, A dot synthesized. And what about B? B dot, it is getting from its inherited value, it can be from its sibling, right? So again it can be of inherited. Getting? If it is getting from the parent, then it is synthesized. If it is getting from the sibling, then it is inherited. This is the difference between your synthesized attribute and your inherited attribute, right? So if you want, you can if you want, I can explain it to you again. This is very important. Why? Because all our methods in the next coming classes will work in this way. Alright, so I'll help you in understanding again. So synthesize attribute, what does it say? I have one root node with, because synthesize work from root, within itself and to its child. So I have a root node here, and these two are sibling node, child node. So here this node is A, this is B, and this is C. How synthesis work is, so synthesis, that is A dot synthesized, can get the value from A dot inherited. A dot inherited. Okay, that's the condition which I am solving with itself. If it is getting from itself, then it is from inherited value. The other thing is, it can also send the value to the children also. So how about it? So C dot synthesized will be equal to A dot synthesized. Okay, this is how the terms works, right? From itself and towards its children. The next case is, this is the case for my inherited attribute. So inherited, as the name suggests, I'm getting from the parent to child. So I have a node A, I have B and C as child. A is parent, B and C is child. So what does it say? Inherited attribute. Inherited attribute should get from the parent, one case, or from its siblings. So if the node which I am speaking is C dot inherited here, so let me write here. So C dot inherited. So C dot inherited can get the value from A dot synthesized. A dot synthesized will be the parent. A dot synthesized. What about the other case here? C dot inheritance can also get the value from B dot inherited. B dot inherited. So these are the cases. But as you can see, with the inherited value, I cannot send to its child. That's the only point which you need to be quite familiar with. Alright. So I hope you people understood about the synthesized attribute and this inherited attribute here. So let me go through the terms here. Inherited attribute for a non-terminal B is a parse tree node n is defined by the semantic rule associated with the product at the parent node, that is n. Note that the product must have B as a symbol in its body. Of course, no issue with that. An inherited attribute at node n is defined only in terms of attribute value. This is important. With whom? One, it can be from the parent, and the other one is with respect to siblings. Alright, so the next example here gives you very clear cut information about the understanding here. And what does it say? So synthesize here is, I have a node and I have C, so it's a single child. So how does the synthesized work here? From the value of C towards n, right? So it can get the value from its child towards its parent, right? So if that is the case of single child. So if I have two things here, so again you can see this is about the synthesized. So node, I have child 1 and child 2, anyhow the same way, getting from two child, in the sense this is from the left child, how I am getting, this is from the right child which I am getting, no issues with that. The other thing is either from itself, so itself in the sense from synthesis towards the node itself, that means value can be transmitted itself, right? And with the inherited value here, so inherited value is 1 itself, sibling, and getting the value from the parent. So from the parent to the child. So here if you can see the arrow mark, from child to parent it is. So in inherited, from P to N, that is from parent to the child. Alright. So one is with the parent, this is about the parent. The second thing is node under consideration, probably within the value of the node itself. The second thing is sibling. Sibling means from its it can be the other child to the same parent, right? So getting the information from the other child to the same parent is what about the sibling, which you can see here. So these are the ways how exactly synthesized and inherited works. So here inherited is from the sibling here, and this is from the parent, from both parent and sibling, right? So better understanding will be obtained once you people look into a few examples. So before going to those examples, we have few definitions to understand. So terminals can have, terminals in the sense the last leaf nodes can have the synthesized attributes but not inherited attributes. That should be quite clear, right? So why exactly we need to be, it needs to be the synthesized attribute. A small example, let's take a node as A here, and I have B as one child and the other thing as C. So if it is inherited as this is my last node, or in the sense I call it as a terminal, or the other name is leaf, right? So if it is a leaf, if I consider inherited, so inherited according to the condition is what? One is with respect to sibling, fine. The other thing is it needs to get the value from its parent. It needs to get the value from the parent, but still, how will this get the value, right? So here, if this is a parent itself, then it will be of no use. Why? Because if it is inherited, it needs to get the value from the parent, but if it is synthesized, it will go from the other way around. So we need to be working with the other way around, that is from the child towards the parent, because ultimately in the root is where I need to get my the value should be pushed towards the first particular node or towards the starting symbol. That's the only rule here. So inherited cannot be there in the terminals, right? It will always be a synthesized, so that if it is a synthesized, it can always push the value towards its operand. All right. So S attributed SDD refers to, okay, there are two types of SDD. One is S attributed and the other one is L attributed. So S attributed is syntax directed definition that involves only synthesized attribute. That means I have only synthesized attributes present in it. I don't have L attributed. So then it is called as a S attributed SDD. In S attributed SDD, each rule conjugates an attribute for a non-terminal at the head of the production from attribute taken from body or production. So here, so what does it say? Each rule is used with an attribute for the terminal at the head of production from attribute taken from body or production. As we know that within the synthesized, it is from child towards the parent. The value or the data travels from child towards the parent. So that's why in the SDD of S attribute, it will always be from the body of the production towards the top. So S attributed SDD can be implemented naturally in conjunction with the LR parser or bottom up parser. So bottom up parser is where we start from the input, from the leaf, from the input towards the starting symbol, right? So that's about the bottom up parser here. Okay, one extra information is we have annotated parse tree. So what do we know about the annotated parse tree? What are the characteristics of annotated parse tree? Is a parse tree showing the values of attributes, right? It's called as an annotated parse tree. Basically, in my parse tree, if I have dot some attribute, it can be a value, or it can be a lex value, or it can be any other value, right? So any other attributes, in fact. So that makes it as an annotated parse tree, right? So, and one more thing is, in this annotated parse tree, we always go towards the bottom up parser. Why? Means I have all my values towards the end of my bottom, right? So bottom within the parse tree. So order of evaluation is post order traversal, example of S attributed syntax directed definition goes in this way, right? So I have a production L tending to En, and E can be E1 plus T, E can be tending to T, T is tending to T1 star F, T tends to F, F is tending to within brackets E, and F tending to digit. So these are my productions, right? So in the productions, which are the terminals here? The one important terminal is my digit here. Open bracket, close bracket, star, plus. These are my terminals, and the remaining whatever I have towards the left hand side, they are all called as non-terminals. So with respect to S attributed SDD, only synthesize related attributes will be pushed, right? So L dot val will be equal to E dot val, and with respect E tending to E1 plus T is E1 dot val, T dot val. So we just substitute the value attribute towards the each entry here, right? So F dot digit will be F dot lexical value. Why? Because this is the input which we get from the lexer. The other term here is L attributed STD. L attributed in the sense I have inherited values also, right? So example of mixed attributes or L attributes STD here refers to, instead of just only synthesized, I also have inherited value also. So here, if you can look into this term, T tending to FT dash. So T tends to FT dash. One thing is you should always find out the value of new term, inherited value, as well as with the synthesized value. That's the rule here. So T tending to FT dash refers to how do I get the value towards the rightmost term. So which is my rightmost term here is T dash. So T dash, as it has a sibling towards its left. So inherited is where we start. That's how it works, right? So which is my right term here? It is T dash. T dash, if it is having a left term, or usually with respect to the sibling is what we work out. So T dash inherited will be equal to F dot val. Whatever I have with F here, that value will be pushed towards the T dash dot inherited. You need to find out this semantic rules you need to find out, only then you can solve with respect to upcoming problems, right? So T tending to FT dash is where T dash dot inherited refers to, it needs to get the value from its parent or by its sibling. So if sibling has some value, because F is giving me the digit, so T dash dot inherit will be equal to F dot value. Fine. So next is, what if this value, from where to where I push the value? From F dot val I push the value to T dash. So how will this T get the value? T should get the value from T dash. That's what T dot val will be equal to T dash dot synthesize. I hope you people understood it. So next case is T dash tending to star F T dash. So here, what do I know? From where should I start? Start from the right hand side. So T dash. So again, so anyhow, with respect to this case, we already have given the value for T dash dot inheritance, right? T dash dot inheritance is getting the value from F dot val, right? So what is the other term which we are missing out now? In order to differentiate this one is T1 dash, guys. This is not just T dash, this is T1 dash. Okay, so this is T1 dash dot inherited is getting the value from T dash dot inherited, that is this one, T dash dot inherited into F dot val. Okay, so you might ask the question here, why exactly we got T dash dot inherited? Because we have a value of star here. How will I get the value if I just replace it? So I am getting the value from my T dash dot inherited star F dot val. Okay, so here I got the value of t1 dash dot inherited. So ultimately, what is the value which I'm looking for? I'm looking for t dash. So t dash dot syntax, sorry, dot synthesize is getting the value from t1 dash synthesized. As we know that synthesize can get the value from synthesize only. The next term is we have t dash tending to epsilon. So t dash tending to epsilon refers to t dash dot synthesize is getting the value from its inherited value. So f dot val is of course digit dot lex val is where I'm getting the value from my lecture. Okay, so yeah, so SDD which has both synthesized and inherited attribute is called as L attribute SDD. It is used in top-down parsing, and order of evaluation is with respect to the topological sorting. So the next evaluation order for SDD is a dependency graph is used to determine the order and computation of attributes. While an annotated parse tree shows the value of attributes, a dependent graph helps us to determine how those values can be computed. So next is about how do we deal with respect to the dependency graph. A dependency graph predicts the flow of information among the attribute instances in a particular parse tree. So we have a problem which is coming within the next. If we have how exactly we generate the parse tree, and how do we how does the value flow within the parse tree is what the dependency graph here states. So an edge from one attribute instance to other means that the value of first is needed to compute the second. For each parse tree node, there is a node X. The dependency graph has a node for each attribute which is associated with X. So if the syntax rule associated with product P defines the value of synthesized attribute A comma B in terms of value of X, then the dependency graph has an edge from X dot C to A dot B. And of course we'll come back to this particular steps. Let's take a production where I have a production E tends to E1 plus T. So you know the drill now. What are the things which we need to do? So what does the semantic rule refers? E dot val will be equal to E1 dot val plus T dot val, right? So we got to understand this. So what exactly is E dot val? This is ultimately the answer which we are looking for. E dot val is a synthesized from E1 val and T val. How exactly? So I have E1 dot val plus T dot val. So this E1 dot val, it adds with the value of T dot val, and it here the value of E dot val will be generated, right? So looking into one very important example here. Yes, let me. Okay, so I guess this is quite simple. Okay, viewable. Next is yes. So I have productions. T is tending to F T dash. T dash is star F T dash. T dash tend to E, and F is tending to digit. So you generates the particular SDD, or in other words, something called as T attributed SDD. So where I have both synthesized as well as inherited. So what is T dash? T dash dot inherited value. T dash dot inherited value will be F dot val. So ultimately T dot val will be from T dash dot synthesized. Alright. So here T dot synthesized is getting value from whom? So T dash dot inherited. Right. Basically we'll see into the diagram. So T dash is tending to star F T dash. So what is the case here? So this is different. This T dash is different, right? In order to differentiate, we'll take it as T1 dash. We'll take it as T1 dash. So here that is missing. So T1 dash inherited will be equal to T dash dot inherited into F dot val, right? So T dash dot inherited, we got it. So inherited is the value which we don't want, because I cannot send it towards the root or the other way around, right? With the inherited value I cannot move the value from bottom to top, right? With the inherited value it is from top to bottom and from its sibling. Getting? So here, so what happens with t dash tending to star f t dash? 1. So t1 dash dot inherited is getting the value from t dash dot inherited into f dot val. So t dash dot synthesized is getting the value from t1 dash dot synthesized. So that's about this case. Fine. So this is anyhow t dash is sending to epsilon refers to one simple sentence, which is t dash dot synthesized is the same value as that of t dash dot inherited. So f tending to digit is f dot val will be equal to digit dot lexical val. Okay. So for this we need to generate the result, right? So how exactly it looks if we represent this particular semantic rule in a dependency graph. So ultimately, which is the value which I need? I want t, right? So t is what? T is t dot val, right? And how exactly will be moving, right? I'll draw the case here. I'll draw the case, and anyhow, remember that it's a bottom-up approach. So from digit I need to start, right? So how do I get digit at the end? So I start with t. T is tending to ft dash. So one side I have f, on the other side I have what? I have t. So it is t dash. So it is t dash here. All right. So in the other hand, I have f. From f, any production leading to digit? Of course. From f, I have the digit here. So digit. Next I have t dash. So t dash is giving me star ft dash. So star f t dash. Star, this is f, this is t dash. Okay, so again t dash is giving me what? T dash is giving me epsilon. What about f? F is giving me again digit. So this is the basic parse tree, right? This is just a parse tree, but this is not a dependency graph. So how do we make a particular parse tree into dependency? Is where is my ultimate value from bottom to top approach, right? So I start from the digit. So what is digit? Digit is a lexical value. Digit is a lexical value, right? So ultimately, what about this digit? This digit is also lexical value, right? This is our first step. Starting from bottom to top, that means identify the terminal. Anyhow, I don't deal with respect to epsilon. So here I start with the value of left to right. So this will be my first step. From here I send the value to f. So this is my value of second step here. And the other thing is, do I have any other digits? Yes, I have another digit here. So this will be my second step. So from first digit I send the value to f. So this is my third, and again sending it towards its regular non-terminal. So this will be my fourth step. This is where the things gets a bit more difficult, right? So here what do I do with the f value, right? So now f value, which should be sent towards what? F dot val should be sent to t dash dot inherited. So here with this case I have two things now. One is with inherited, that is t dash dot inherited, and the other case is t dash dot synthesized. What was the rule? Rule is in synthesized, the value should be moving from child to the parent, with the synthesized, or the other case is itself, the value can get it by itself. Getting? So ultimately, what is the value which I am looking for? T dash dot synthesize, but T dash dot synthesize should get the value from T1 dash dot inherited, right? So this value should get from inherited. Then what is the value of T dash dot inherited? From where am I getting the value of T dash dot inherited? As we know that with inherited terms, it is the other way around. That is from parent to child, and from itself as well as from the sibling, getting a very long jump, that is from sibling, right? So these are the property of inherited, but never the value will be going from the child to the parent when it comes to the inherited. Getting? And okay, so as these are the two properties, so inheritance has three properties, synthesized has two properties. So here T dash dot inheritance will get the value from your f dot val. So ultimately what do I have here? I have f dot val. That means here I have fourth step. So this will be f dot val to T dash dot inherited. This is my fifth particular value here. So this is my fifth step. Okay, so from inherited, I can get the value from synthesized. Why? Because I can get from the itself value. So from syntax, from okay, so before getting to this here, before getting to this value, and synthesize will go up, I need to give the value from inherited towards my I need to calculate this t dash value, right? So here, this from the step 5, the value will be, that is t dash dot inherited will be sending the value to its t1 dash dot inherited, so this is my sixth step. The seventh step is I get the value from f also here, so this will be my seventh step. Okay, so the seventh step is inherited. So again, from inherited to synthesize, this is my eighth step. From synthesize towards the main root function, this will be my ninth step. So here every step is actually following this rule of synthesize as well as with the inherited attribute. Alright, so this is about one very good example of letting to know the, if you include any of the the synthesized and the inherited attributes, then it becomes the dependency graph. Alright, so every time you just look into it, how exactly these things are actually tabulated. So this parse tree, or sorry, the dependency graph here has been constructed using the particular semantic rules of the production. Alright, next, moving on, order of the evaluation of attributes. So here, if the dependency graph has an edge from node m to n, then the attribute corresponds to m must be evaluated before attribute of n. So looking into the examples, we'll be knowing about it. So thus the only allowable orders of evaluation are those sequences of node from n1 to n5. If there is an edge of the dependency graph from ni to nj, then I should be less than j. Such an ordering is called as a topological sorting of a graph. If there is any cycle, then no topological sorts, that is evaluation of SDD, is not possible. So condition here is if I have any cycle within the topology here, my SDD is not possible. So for dependency graph, within the previous page is the topological sorting from which are the steps which it goes, right? So ultimately I should not have a cycle. That means if I have cycle here, then SDD is not possible. Alright, then next is S attributed definitions. SDD is S attributed if every attribute is synthesized. When SDD is S attributed, it attributes evaluated in any bottom-up order of nodes of parse tree. We can have post-order traversal of parse tree to evaluate the attributes in S attributed functions. So how does the post order work? Post order of any n works with respect to each child c of n from the left towards the post order of c. Alright. Moving on with S-attributed definitions can be implemented during bottom-up parsing without the need of explicit create parse tree. Okay, so let us move towards the problems here, right? So we can always come back, right? This is a small example where we have some values which is put up towards the digits, right? For the same production which we saw in the upper production, upper example, right? So look into this example here. For the input 3 star 5 plus 4n, generate the SDD, right? This is how example or the problem will be asked in your main exam, and they might also, without giving this production, right? This is also possible. Without giving this complete production, they might just give you this question, right? Write the SDD for simple desk calculator, right? So this is a one line questions which is actually yielding towards 7 or around 8 marks, 6 marks, right? This is a question. They won't give you much. They only ask for write a SDD for simple desk calculator. You need to write the production. You need to take an example of an input. You need to write the semantic rule, and ultimately you have to write the next particular tree structure, that is the parse tree, right? So that the dependency graph, right? So that is the ultimate thing. So remember this particular production every time. This is very important, right? So as this is a common question which can be asked, and the other question which can be asked is e tends to e plus t minus t. That's a repeated question which we have seen a number of times. So say, or the questions might arise similar to it. So production goes in this way. Ultimately the value should be reaching towards my starting production, that is with respect to the alpha. So alpha or L is tending to En, so L dot val is equals to E dot val, E dot val equal to E1 dot val plus T dot val, the same stuff here, right? Ultimately in the digit we have something called as lex dot val. How does my annotated parse tree looks here? So looking into the terms of production as well as the thing here. So what is the input? Input is 3 plus 5 plus 4n. 3 plus 5, sorry, 3 star 5 plus 4n. Okay, so looking into the term here, so I have 3 star 5. Let me start with L. So I have to start with L. So L is giving me what? E. So L is giving me E, and it is also having some number n. Next is E is giving me E1 plus T, or E is also giving me E plus T, but plus is on the other hand. We always need to go towards the left hand side, but E has only production because I need plus somewhere. So this E will be synthesized to E1 plus T, E1 plus T. So what do I want? I want 3 in the beginning, from if I'm using from left to right. So 3 is what the digit value which I want. So do I have anything related E1 to 3, that is digit dot val? So E1 or E has a production with respect to T, T to F and F to digit. So E1 to T, or E1 in and E both are the same. In order to differentiate between two E's here, I have taken it as E1, that's all. So E is tending to T and T is tending to, oh, I have a term of 3 star 5. So I need to utilize this production, not straight away go to F. If I go to F, this becomes a dead end of 3 alone, 3 plus 5, then this input will not work. So T is tending, I have a 3 star 5. So 3 into 5. So I need to go with the production T1 star. This is T1 star F. So again, differentiating this T and this T is, I'm making this as T1. So this is star, and ultimately this is my F. So I have a production T tends to F. So this T is giving me F, and F is having digit. So I have digit. Alright. So here F is giving me what? F is giving me digit. So ultimately digit star digit, digit star digit plus, again I have digit n. So T, T to F, and F to digit. This is the exact tree which we are looking for. This is a parse tree with its attributes. Parse tree with its attributes is called as annotated parse tree. As simple as that. So E1 dot val, so T dot val, everywhere if you insert val, then it becomes annotated parse tree. So this is how exactly it looks. If you can see here, the same thing has been written, right? The only thing is I'm missing out few numbers here, so let me take out. So what was the number? 3 star 4, sorry, 3 star 5 plus 4 n. So this digit is 3. This digit which I have is 3, and this digit is 5. So this digit is 5. So here what will be my f dot val? F dot val will be equal to 3. So here f dot val will be equal to 5. So t dot val will be equal to 3. 3 into 5 is 15. So t dot val is 15. So 15 plus this val is 4. This 4 will be pushed. F dot val is 4. So 15 plus 4, this 4 will be pushed to t dash dot val. So here I have 4, and here I have 15. So 15 plus 4 is 19. So 19 n. So ultimately the result which we are looking for is 19 n. This is how the annotated parse tree looks like, right? So giving the value for the annotated parse tree is yielding us with the result, right? So the next case is we want dependency graph. Ultimately dependency graph is what we are interested in, right? So few cases are my values here move from one place to another, right? Let's check out with respect to how we are we obtain the value of this, right? So digit is, where did I start with this term? I started with 3, right? 3 I started, 5 I started, right? From 3 I moved towards the t dot val, right? So here I start with the digit val which is 1, right? So getting the value or giving the value to f dot val, that is my step 2. Giving it towards t dot val, that was step 3, right? So ultimately I also get the value from the other number also, from 4 to 5. From 5 to 6 is what I did. So here getting the value of t dot val and f dot val, multiplying it, and value I got it here. So this is my 6th step. So what did I do? I pushed it towards the top so that my leftmost derivation is completely done. So again getting the value from 8 towards f dot val, that is 9. From 9 to t dot val, that is 10. And from 10, from this 7 and 10 value, basically this is 11, right? The same step, both the steps are the same. Alright, so this is my 11th step, and from the 11th step what did I do? I went towards the other value, that is L dot val. So L dot val is ultimately 19 n. Alright, so here if you look into the topological order here, 1 2 3 is what? The other way it can also be written. So here 1, so again this is 2, right? So within my previous example how we did is I get the first value from all the digits, from all the lexical value, right? So the thing here is I should not have a loop. A loop will yield my property here towards it's not in an SD, right? If I have any loops here, that doesn't give me with respect to the STD. Alright, so I hope the example was quite simple and quite clear for you guys, and I want you people to write the particular annotated parse tree as well as with the directed graph, right, for these 3 examples. So this will be your assignment for today. So kindly send me the particular assignment and the homework for these questions, so you can take a screenshot and you can send it to me, right? So regarding the other examples, we shall work tomorrow. All right.